Swayam Prabha. Digital India. Educated India.
How to derive similarity equations and solve these equations to obtain friction factor and Nusselt number for two-dimensional laminar boundary layers. We now move to the next method, that is the integral method for solving boundary layer equations. The task for this lecture, therefore, is to derive the integral equations of a boundary layer. The development of firstly the integral equation for a velocity boundary layer, and then the integral equation for a temperature boundary layer. Equations and solve these equations to obtain friction factor and Nusselt number for two-dimensional laminar boundary layers. We now move to the next method, that is the integral method for solving boundary layer equations. The task for this lecture, therefore, is to derive the integral equations of a boundary layer. So, we shall begin with the development of firstly the equation for a temperature boundary layer. The integral method represents a class of approximate methods capable of handling arbitrary variations of u infinity, suction or blowing velocity V w, and wall temperature variation T w. In this respect, the method removes, you will recall that similarity method permitted only certain types of variations of the free stream velocity, the wall velocity, and the wall temperature variations. The method is called approximate method not because its equations are approximate. So, the method actually derives exact boundary layer equations, but in integral form rather than differential. It is the solution methodology which is approximate and not the equations, a point very important to remember in all further development. Unlike the similarity method, this method is attractive because at least in some simple cases, closed form solutions can be obtained with little algebraic effort. In this sense, at one time people used to call the integral, because you could do all the calculations on a by simple algebra without having to go to a computer. The second advantage of the method is, of course, that it can now deal with any arbitrary variations of u infinity, V w, and T w. So, let us first of all consider the boundary layer du by dx plus dv by dy equal to 0, and the convection terms or the momentum transfer terms, and the pressure gradient term, and the viscous term. These equations are integrated term by term with respect to y of the boundary layer from y equal to 0, where u is equal to 0 and v is equal to v w, to y equal to L, where u equals u infinity and v equals some fictitious velocity V L. L is greater than the delta max in the region 0 to L, as you will see on the next slide. This figure shows a surface on which a boundary layer grows. Of course, a boundary layer development can be uneven. The boundary layer can grow, then shrink and then grow depending on the pressure gradient that is applied. And when u infinity varies arbitrarily with x, of course, the boundary layer thickness too will vary arbitrarily with x. But we always choose to analyze a boundary layer over a given length L, and in this length L, we make sure that we choose a dimension del L which is greater than delta max in this region as shown here. Continuity equation, then term by term integration will give 0 to L du by dx dy. This term will simply reduce to V L minus V W, and this term is taken to the right hand side as minus d 0 to L du by dx dy, and I can take the differential out and write it as minus d by dx of 0 to L u dy. You will see then that V L minus V W simply represents the change in the flow rate in between two successive stations. V L is a fictitious velocity at L, and V W x is the familiar suction or blowing velocity. Likewise, if I were to integrate momentum equation term by term, then you will see 0 to L d by dx of u u, 0 to L d by dy of u v equal to 0 to L u infinity du infinity by dx dy plus nu times du by dy square dy. Then this term, taking the differential out, will simply d by dx of 0 to L u u dy plus this term will become u infinity V L minus u w V W equal to, remember, this is not a function of y, u infinity du infinity by dx is not a function of y, and therefore can be taken out, and integral 0 to L dy would simply yield L, whereas this in term would integrate to nu times du by dy at y equal to L minus du by dy at y equal to 0. But notice this term will vanish because u w, suppose that u w is equal to 0. So, that term goes to 0. Likewise, du by dy at L is also equal to 0, and the term that survives is mu by rho du by dy at y equal to 0. But mu into du by dy at y equal to 0 is nothing but the shear stress divided by rho, and that is what you see on the right hand side here. This term is represented here. I have replaced V L into u infinity as V L from the previous result as shown here as V W minus d by dx of u dy, and then of course, this term survives. So, we move further. Remember, u infinity du infinity by dx L is nothing but u infinity du infinity by dx 0 to L dy, and since u infinity is not a function of y, I can absorb it inside the integral and write it as du infinity by dx 0 to L u infinity dy. Then read as the first term here, u infinity into V W minus d by dx u dy as before. This term is now replaced by that du by d infinity is minus tau of x by rho. Now, consider the identity d by dx of a product of integral by dx integral 0 to L u dy plus u infinity d by dx integral 0 to L u dy, and this is precisely the term you see here. So, I am going to replace here. If I do that, then you will notice that I can write this equation in this manner: d by dx 0 to L u into u minus u infinity dy, which is this term, plus du infinity by dx into 0 to L u dy, which is this term, and then this term which is minus u infinity into dy, and then minus tau all rho x by dx, minus tau all x divided by rho, and minus u infinity into Vw. So, if I divide and multiply each term by the same quantity, meaning if I multiply this equation by u infinity square and divide by u infinity square, if I multiply this equation by u infinity and divide by u infinity, then you will notice I can write the equation in this manner: d by dx of u infinity square u over u infinity into u over u infinity minus 1 dy plus u infinity du infinity by dx equal to 0 to L u over u infinity minus 1 dy, and all this. But recall that this integral is nothing but our minus 2 or the momentum thickness, and this term is nothing but minus delta 1 or the displacement thickness, and therefore, this term will become minus d by dx u infinity square delta 2. This term will become minus u infinity du infinity by dx into delta 1 and 2 terms. So, cancelling the minus sign which appears in each term, we would have the equation which looks like this: d by dx u infinity square delta 2 plus u infinity du infinity by dx delta 1 equal to the shear stress term and the suction and blowing term. I will further manipulate this equation as shown on the next slide. So, if I divide through by delta u infinity square and open up this differential of a product as u infinity square d delta 2 by dx into delta 2 into du infinity square by dx, then you will notice that the equation will read like this: d delta 2 by dx plus 1 over u infinity du infinity by dx into du delta 2 plus delta 1 equal to Cfx by 2 plus Vw by u infinity. So, each term now is dimension, so is x. U infinity and u infinity has the velocity dimension, delta 2 and delta 1 have length dimension, so is does x. So, the term is dimensionless, and so are the terms on the right hand side completely dimensionless. It is this equation which is known as the integral momentum equation. It is an exact equation because we have not introduced any assumptions in its derivation. We have simply integrated the partial differential equation from 0 to L, because all quantities vary only with x. So, the partial differential equation of the boundary layer is converted to an ODE for an integral parameter delta 2. This is very similar to what we did in similarity method, where the PDEs were converted to third order ordinary differential equation. Here the equations are converted to a first order ordinary differential equation for an integral parameter delta 2. Cfx is the coefficient of friction, and that is simply defined as tau all x over rho u infinity square divided by 2. So, this is well known to you. So, this then is the integral momentum equation. There is another variant of the equation which is called the integral kinetic energy equation. It can be derived from the earlier momentum equation, but I will derive it from first principles. So, recall our momentum equation reads like that, where these are the terms. If I multiply each term by u divided by rho throughout, then you will see and define E as u squared by 2, then you will see this term simply can be written as due by dx. This term can be written as dve by dy, equal to u infinity du infinity by dx plus nu u d2u by dy square. I repeat, E is the energy of the actual velocity u squared by 2. Again, if we integrate this equation from y equal to 0 to y equal to L or delta, it does not really matter what we do, then this term will simply become u into u squared by 2. So, that becomes u cube by 2 d by dx integral 0 to delta dy. This term will be V e at delta minus V e at y equal to 0, but at y equal to 0 u is equal to 0, therefore, E is equal to 0 and that term will go out. So, the V L into E at L or infinity is simply V w minus d by dx of 0 to delta u dy u infinity square by 2. This is the value of E infinity, and that would equal du by d infinity by dx. U is now u is infinity is absorbed inside the integral dy plus nu integral 0 to delta u d2 u by dy square dy. It is this last term which I shall because this is just an result on the next slide. So, integration by parts will give nu 0 to delta u d2 u by dy square dy equal to minus nu d 0 to delta du by dy whole square. So, now in the integral kinetic energy equation, we introduce another thickness called the kinetic energy thickness, and it is defined very much like the momentum thickness, except that we now have 1 minus u over u infinity square, which represents the kinetic energy deficit caused by manipulation of the previous equation, which is shown here. You will see that this can be manipulated to read as du by dx of u infinity cube delta 3 equal to v w u infinity square plus 2 nu du by dy whole square, which is this term. Integral kinetic energy equation is sometimes used in boundary layers, analysis of boundary layers with suction and blowing. We now turn to integral energy equation. So, again consider the boundary layer, the surface on which a boundary layer is developing, and this solid line represents the velocity boundary layer. But now, the thermal boundary layer will have a thickness either greater than the velocity boundary layer thickness or smaller than velocity boundary layer thickness. And you already know from your similarity solutions that when Prandtl number is greater than 1, the thermal boundary layer thickness is smaller than the velocity boundary layer thickness, whereas if Prandtl number was less, boundary layer thickness is greater than the momentum the velocity boundary layer thickness delta. So, while integrating this energy equation, which includes this viscous dissipation term, we will choose L big enough so that it is either greater than delta for case of Prandtl greater than 1, or it is greater than thermal boundary layer thickness capital delta for Prandtl number less than 1. We define for convenience theta equal to t, where t infinity is constant with x, but t wall is some function of x, and I will introduce that function shortly. So, then this equation will simply become this term will become du theta by dx. Additional term arising out of the fact that t w now is a function of x, and therefore, you will have a term called by t w minus t infinity into d by dx of t w minus t infinity. This term will become alpha delta 2 theta by dy squared, and this term will become nu Cp Tw minus T infinity du by dy whole square. It is this equation that we shall integrate from 0 to L, where L is greater than delta max for Prandtl equal to 1, Prandtl greater than 1, and L is greater than capital delta max for Prandtl less than 1. So, let us do the integration on the next slide. You will notice that integration of this will simply become d by dx of integral u theta dy, and if I divide and multiply by u infinity, it will read as d by dx of u infinity 0 to L u infinity u by u infinity theta dy. The integration of this term will simply give V L theta infinity minus V W theta W, and theta W, as you know, is 1. Then you will see V L theta L minus V W theta W plus this term will be simply 1 over T W minus T infinity by dx of T W minus T integral u theta dy, and that is what I have written, and u theta dy I have divided by u infinity and multiplied by u infinity. The diffusion term will simply give alpha d theta by dy at L minus alpha d theta by dy at 0 plus nu whole square dy. Now, if you recall that our enthalpy thickness delta 2 was defined as 0 to infinity u over u infinity T minus T infinity over T wall minus T infinity, then it is nothing but 0 to L u over u infinity theta dy. In other words, this quantity is nothing but delta 2, capital delta 2. Theta L, because of its definition, is 0, and therefore, that term vanishes, whereas theta W is equal to 1. Equal to L is 0, because the temperature gradient at the infinity at the edge of the boundary layer is 0. But see what this term means, d theta by dy at y equal to 0 multiplied by alpha. Well, that d theta by dy will simply be equal to dt dy divided by T W minus T infinity, and therefore, q w into rho C p with a negative sign, and q w divided by T w minus T infinity is nothing but local heat transfer coefficient H x divided by rho into C p. So, this term will be replaced by minus H x rho C p, and therefore, you will see the equation would now read as u infinity d by dx of u infinity delta 2 by dx, u infinity delta 2 into T w minus T infinity d by dx T w minus T infinity into H x divided by rho C p plus V w plus nu by C p 0 to L du by dy whole square into dy. If I divide through by u infinity after opening up this differential, then I would get what is called as the integral energy equation d delta 2 by dx plus delta 2 into the wall variation term into the free stream variation or the pressure gradient term, Stanton x, which is H x divided by rho C p u infinity, as I have shown here, which is nothing but Nusselt number divided by Reynolds number into Prandtl number. We have seen this before. Then the wall velocity variation term V w by u infinity, and then the viscous dissipation term as this one. Each term here is dimensionless. As you can see, this is dimensionless, this is dimensionless, so is delta 2. This is dimensionless, this is dimensionless, and so is this dimension. It can be shown quite easily. So, each term now is dimensionless, and therefore, we have an ordinary differential equation for capital delta 2, analogous to an ODE for small delta 2 in the velocity boundary layer equation. So, let me summarize all the equations that we have derived. So, integral continuity equation simply gives V L minus V W equal to minus d by dx of 0 to L u dy. The integral momentum equation gives variation of d delta 2 by dx as that, and accounts for the wall velocity, and the integral energy equation gives the rate of change of enthalpy thickness delta 2 and accounts for the wall temperature variation, the free stream variation, and wall velocity variation, and the viscous dissipation. Our interest always would be to determine Stanton x and CFX. So, with this, I will take up in the next lecture the solution of the velocity boundary layer equations in their integral form. Thank you.